Hello everyone, especially those STEM students who are watching this lecture video. So, I just want to say thank you for your support for watching the past video that I posted, which is about the topic one about the basics of chemistry, about matter and its properties. And um, I just want to say thank you for supporting and I hope that you continue watching the lecture videos that I'll be posting here in this channel and I hope that it would be a great help for everyone that having difficulties in understanding basic chemistry. Before I'll proceed in my second topic. So I think I forgot to introduce myself in the first video. I just do it now so that you will have an idea who is talking in front of you right now. So here, I just want to share my screen. Okay. This is the topic for today, numbers and measurements part 1. So another video will be posted for the part 2 in this discussion. Yes, so I'll be going to introduce myself. My name is Judy Marl Elarmo. I graduated Bachelor of Science in Chemical Engineering last March 2020 only. Uh, I could be considered as a fresh graduate because I just graduated last year and I came from Xavier University, Ateneo de Cagayan. So currently, I don't have um, still my license degree. I hope that next year it would be a success. So me and my batchmates are working hard to earn the degree and I mean to earn the license and then um, hopefully it will be given to us next year. So currently also I'm working as a chemistry part-time instructor here in one of the most well-known university in the city. So this is my first job after I graduated. So I'm glad that I've given a chance to discuss my my knowledge in chemistry to every one of you, and I really hope that it would be a great help. So let's get started now in our discussion. For our discussion overview, I'll be discussing two main topics or areas in our discussion on numbers and measurements. First is the chemistry measurements and numbers. So I'll be introducing to you measurements in units, and then we try to understand the difference between accuracy and precision. Also, we will do some problem solving involving significant figures. But before that, I just want to discuss to you the rules behind significant figures and why is it necessary. And then also the concept on scientific notation. And after that, we do the problem solving and then we do some conversion using conversion factors or appropriate ratios from one unit to another and also to apply the correct significant figures in our final answers. So here, what can you see in the picture? Of course, you see different measuring devices. These measuring devices is it's based on its use. So here we have measuring devices for volume. We are familiar, I think, for burette, for pipette, graduated cylinder, and then volumetric flask. And here we also have measuring devices for measuring the mass. So this is example of electronic weighing scale or weighing scale used in the laboratory. So these are different measuring devices that we currently use in our laboratories. So, there are still many measuring devices, but I just input these measuring devices here. So what is really measurement about? So this is a process of obtaining numerical or data. Obtaining numerical or data from experiments. So we have a lot of measuring devices that the main purpose is for us to get some readings or get some measurements to get valid values for our experiment. So here for if we want to get the mass, we will be using this instrument or measuring device, and then we could get a value, for example 10 kilograms or even 5 grams, or in terms of different units that is related to mass. And then we also have length. We usually use rulers or measuring tapes, and then you could get values like 1 meter, 0.5 centimeter, and anything that is related to length. And then we also have time, so we could get these readings in terms of seconds, hour, and yes, measured items. Measured units for time. So what are we basically measuring? So we are measuring physical quantities here in chemistry. So these are the properties that of a certain material or system that can be quantified by measurement. And this can be expressed as a combination of a numerical value with a unit. So we have two types of physical quantities. We have base quantity and derived quantity. So for base quantities, we have these are the physical quantities that cannot be defined in terms of other quantities. So here in this table, we have given these base quantities with their corresponding SI units. So for length, we have in terms yung units is in meters, mass is kilogram, and then time is per second, temperature is Kelvin, and then electric current is ampere. We also have derived quantities. So these are the physical quantities that are derived from combinations of base quantities through multiplication or division. So example for here is that we have volume, density, velocity, force, and acceleration. And these are their units. So as you can see, for volume, it's a combination of three measurements for length. For density, it's division for the mass, and then also the three quantities for length. For velocity, it's meters per second, so length per time, per unit time. And then for force, we have Newton. Acceleration, we have meters per second squared. So these are example of derived quantities. So now we go to observations. So for our measurements, we usually have some observations on this in our data that we gathered. So and these measurements, you could assess them in terms of the quantities of preciseness and accurateness. So we will define the difference between accuracy and precision. So accuracy, this tells us how close the observed value is to the true value. So in accuracy, we usually set a value as our standard value for our readings, and then we compare that to our measured values to the standard value if how close or how proximate we are to each other. And then this is important because this could measure how our values are reliable, and they are also can be processed by others. So also we have precision. So precision, these are the spread in values obtained from measurements. So this precision, we can measure if our values can be reproduced to other process. So precise measurements, they are highly reproducible. So we could see if the values are far from each other or they are close to each other. So even if the measurements are not near to the correct value, as long as they are quite close to one another. So the question is that, is it possible to have, to be precise, but also inaccurate in our measurements? Here, this is an illustration. So this is a dartboard, and then the center in this dartboard is the true value or the standard value. And then these black dots here is our measurements or our readings. So in figure A is that, as you can see, the values are close to the center, and the values are not also far from each other, so they are quite close. So these readings are accurate and precise because, as you can see in the picture, they are close to one another and they are close to the center, which is the standard value or true value. For letter B also, as you can see, the values are also not that far from one another, but they are far from the center, or they are far from the true value, meaning the values are precise, but they are not accurate. So we have answered our question that, is it possible to have precision, but also being inaccurate? So yes, you could have readings that are precise, but also not accurate. For letter C, as you can see, we have the values spreading out. They are far from one another, and they are also very far from the true value or standard value. So meaning the measurements are not accurate. They are also not precise. So this is the one that we don't want to follow our measurements. So as much as possible, we want our measurements to be accurate and precise, so that we could rely on our readings, and we are confident that we could use them in our calculations, and then you could reproduce them to further experimentation. Also, measurements contains one of two types of error. So we have random error and systematic error. A random error, this make the measurement randomly too high or too low. So I highlighted here random. I have here highlighted here randomly, which is too high or too low. So the measurement here are fluctuating from one another, either very high or very low values. So these random errors are usually caused by variation associated with equipment limitations, and they differ. They just differ slightly from one another. So it comes unpredictable changes during the experiment. So you can get rid on this random error by taking repeated measurements to obtain an average value. So that's the thing that you need to do to eliminate random error. And after getting a lot of readings or repeated measurements, and you get the average value, you can make a plot or a graph to establish a certain pattern. And then after that, you obtain a line or a curve for best fit. And in that way, the discrepancies of your errors are reduced. So, but I will not be discussing how this will be eliminated. I just inform you that you could get rid of these errors in your experiment. Also, we have systematic error. So this make measurement consistently too high or too low. So as I highlighted here the word consistently, because most of the values follow a certain trend. All of them are consistent in being high, and also being very low. Then these are repeatable errors usually associated with faulty equipment or even flawed experimental design. So it always affects the measurements on the same amount or by the same proportion, provided that the reading is taken on the same way in the same time. So uh, to get rid of systematic error, you just need to be more direct in your experimental design. So you just need to be to have a flow process that is very reliable or tama jud na siya na process, and then you also have to use calibrated equipments to eliminate any parallax errors. And then you should know that in working in this experiment, you just your main aim is to have a measurement that are accurate and also precise with less of these two types of errors. So another illustration here is that as you can see, we have different graphs. We have different trial. We have 4 trials, and then in each trial we have readings. So these blue dots here are our measurements or our readings, and then this broken line serves as our true value. So here we will be predicting if the values are precise or accurate. So here for letter A, what can you infer in this figure is that the values are close to 25 grams, which is the true value, and then they are not far from one another. So what can we say is that these readings have high precision and high accuracy. Also, small random error because the values are not randomly taas and then gamay po siya. They are just kanang close to one another. Then also for trial 2, we have the values here. They are far. All of them are far from 25 grams, which is the true value. So you could say that this is not accurate measurements, but the values are quite close to one another. So here we have high precision measurements, and we have low accuracy because they're far from 25, and they also have a presence of systematic error because all the values are consistently in this value very high, which is you could infer as 25 grams. Then for trial 3, as you can see, the values are very spread out. So for trial 3, the some values are close to 25 and some are not. So what can we say here is that this has low precision since they are very far from one another. They also have large random error because the values are scattering, and then they have average value close to actual because I guess these two values are quite close to the 25. Then for the last figure, the last measurement in the trial 4, it's as you can see, the values are really not accurate and not precise. So yes, it has low precision and they have low accuracy. So we have here example problem 1. So Suppose a quality control chemist at a pharmaceutical company is tasked with checking the accuracy and precision of three different machines that are meant to dispense 10 ounces or equivalent to 296 ml of cough syrup into storage bottles. She proceeds to use each machine to fill 5 bottles and then carefully determines the actual volume dispensed, obtaining the results tabulated in table below. Identify whether the results are accurate and or precise. So here, this is the data that the quality control chemist gathered for the three different dispensers. So our true value here is the 296 ml. So we are going to comment if the values are accurate or precise. So what can you say in dispenser 1? So in dispenser 1, none of the values have even reached 296 ml, right? And then but the values are quite close to one another. They differ in just a little amount in ml. So here for dispenser 1, they are precise. The values are close to one another. Within a few tenths of millimeter lang ang difference, but not accurate because none of the values are close to the target, which is 296, each being at least or more than 10 ml too low. For dispenser 2, what can you say? Yes, 296, we are reading here. We obtained the target value, and then we also have other values which are quite not that close to each other. So here, dispenser 2, this improved accuracy because each volume is less than 3 ml away from 296, and worse in precision because the volumes vary by more than 4 ml. For dispenser 3, what can we say is that the values are close to one another, and also a reading here obtained the target value. So some readings are 296.1, usually they differ in a very small value. So I guess dispenser 3 is working well. Dispensing cough syrup both accurately, so the volumes within 0.1 ml of the target value only ang difference, and then precisely because volumes differing from each other by no more than 0.2 ml. So these readings for dispenser 3 is the one that the quality control chemist should follow, or should follow, because the values are both accurate and or precise. Now we go to the concept of numbers and significant figures. So significant figures, these are the digits that are measured in a measured number, or a result in the calculation with measured number that includes all certain digits plus a final one having some uncertainty, or the first digit that we are basically guessing. So the uncertainty here, it talks about the experimenter's best estimate of how far an experimental quantity might be from the true value. So the concept of significant figure is that we just be more precise in our measured number, so that we could get a reliable data, and then sakto siya. These are used to best estimate the data, especially if we use different measuring devices that really needs some estimation. So here we have an example. As you can see, this is the reading. This is the volume reading niya, the instrument. So the water, for example, it's water. The reading is in between 1 ml and 2 ml. So you could not say that the volume the water is on 2 ml because it's not. And then the volume also is in 1 ml because it's also not. So this measuring device has divisions up to one's place. So therefore, the first uncertainty value that we are guessing is the tens place. So here, the tens place is the 0.5 that we are estimating that we are sure or we are certain that the reading is greater than 1 but less than 2 ml. Another example is that here is, I think this is a thermometer, and then by applying also the concept on the measuring devices, the divisions is up to the tens place. Therefore, the first uncertainty value guessing should be in the hundreds place. So you can say that the value is quite greater than 30.2 here. This is 30.1, 30.2 divisions, and then this is greater than 30.2 but less than 30.3 because it doesn't reach here. Okay, but it's kanang nila pa siya gamay sa 30.2. So that's the thing that we need to take into account when we understand our measurements. Then we apply the proper significant figures. So there are rules for significant figures that we must learn. First is that all non-zero digits are significant. So example here is that we have a number which is 111. So this all digits here are non-zero, diba? So this is considered 3 significant figures. We also have 1286. So this is 4 significant figure digits because all non-zero digits are significant. So if we're given 54, we're given 54, this is equal to 2 SF. Then if we're given even if you're given 9, so that's 1 SF. So also we have a rule that zeros between significant figures, they are significant. So example is that we have a number, this is equal to 1001. So these two zeros here are between two significant figures which are 1 and 1. So we count that together with the correct number of significant figures. So this is equal to 4 SF. Then here we have 20,006. This is equivalent to 5 SF. And then if we have 508, this is equal to 3 SF. Because the zeros between significant figures are considered significant. Next is that the zeros preceding the first non-zero digit are not significant. So when you say preceding to the first non-zero digit, the zeros before the first non-zero digits. So we have example for here. We have this value. This is only considered to be 1 SF because the zeros preceding to that number 2 as the first non-zero digits cannot be considered a significant figure. So only this value here. Same for in this value also, we have 3 SF here because these zeros here preceding before 2 is not considered, but we consider this 0 between 2 and 6 because these 2 and 6 are significant figures, considered significant figures. So this is 3 SF. Then we have zeros to the right of the decimal after the non-zero digits are significant. So for example, here we have this value. So by determining the proper significant figures, we don't include these zeros preceding or before the number 3, but we include these 2 zeros to the right of the first non-zero digits because they are considered significant. Also for 9.00, this also considered as three significant figures. For 9.10, we consider this as also three. 90.0 is also three significant figures. Basta all zeros to the right of the decimal after the first non-zero digits. And then lastly is zeros at the end of the non-decimal number may or may not be significant. So we use scientific notation to indicate significant figures. Here, we have a number which is 900. So you could tell that this value here has three significant figures because based on the rules that is given. But we could also say that 900 could be in terms of 1 SF, 2 or 3 SF. So this concept here, we could introduce the scientific notation ngayon to indicate the significant figures. Actually, you can manipulate if your number could have the significant figures that we need to write. So here we have an example problem, number 2. Here, an alloy contains 2.05% of some impurity. How many significant figures are reported in this value? So what we need to do is to convert this 2.05% in decimal places. So it's very simple because you just need to divide it by 100. So by doing so, you could write this as 0.0205. Then in this way, you could determine how many significant figures is reported in this value. So you know that the zeros in between significant figures, they are included in the counting, and then also the zeros preceding to the first non-zero digit, they are not included as a significant figure. So in this value, the correct number of significant figure is only 3, which is the 2, 0, and 5. So I hope that we can understand this. Very simple. So now we go to the concept of scientific notation. So in scientific notation, this is a representation of a number in the form of 8 times 10 to the power of n, where a here is the number or the sign digits only, with a single non-zero digit to the left and of the decimal point, and n here is the integer or a whole number. So to further illustrate this definition, I just want to take into example the past number that we discussed in significant figures, in the significant figure, which is 900. So for example, 900, we know that 900, they have 3 significant figures. Good. But you could express this 900 in terms of 1 SF, 2 SF, and then 3 SF. So you just used multiples of 10 in order for you to multiply the base number, or which is the same sign digit, to express the number in the right scientific notation. So here, in terms of 1 SF or 1 significant figures, 900 can be written as 9 times 10 to the power of 2. So we multiplied it by 10 to the power of 2, which is 100, to achieve the value of 900. Then our A here is 9. So this is only the 1 significant figures that is counted in this form. Also, if we have 2 SF, if you want to express 900 in terms of 2 significant figures, this is can be done in 9.0 times 10 to the power of 2. So again, 9 and 0 is the 2 significant figures that we take into account. For 3SF, we could write 900 by 9.00 times 10 to the power of 2. So we have example here, 300 million. Let's write this in 3 significant figures. So also this value, let's write this in 3 significant figures. So how do we do this? So by doing so, we take note that we only want to write this number in 3 SF. So by doing so, you need to count this in this way. So you need to count how many multiples of 10 that you need to write for you to arrive in this value by giving only 3 significant figures. So we write 3.00 because this is in terms of 3. Then we multiplied it by 10. So what we need to do here is we count zeros. So the first is from here we count. You could also count at the end part, but you could also count here. So let's start here na lang. 1, 2, 3, 4, 5, 6, 7, 8. So here we have 8 zeros. So you multiplied it to the power by 10 to the power of 8 to achieve this value in terms of 3 significant figures. Also, here, if we want to write this as 3SF, so our 3 significant figures would be 3.01 times 10 to the power of. We usually start here in the after the decimal place. So 1, 2, 3, 4, 5, and we stop here in between 3.01. So we need to multiply it by 3.01 times 10 to the 5 to achieve it this value in terms of 3 significant figures. Yes, sorry, that would be the answer. Okay, so let's try in writing these values in terms of 4SF, 3SF, and then 3SF and 4SF. So you could do that. You could pause this video and then do that on your own. So the answer are here. If you get it right, then you really understand the concept of scientific notation. For calculated values, the number of significant figures should be consistent with the data used in the calculation. So what does this mean is that when we applied significant figures using the 4 operations of numbers, so these are multiplication, division, subtraction, and addition, then some rules are also applied. For multiplication and division, the number of significant figures in result must be the same as the number of significant figures in the factor with the fewest significant figures. So here, for multiplication and division, you need to determine which factor has the fewest significant figures. For example, here we multiplied 0.24 kilogram by 4,621 meter. What can you say is that, this value here, it contains only 2 SF, the 2 and 4, and here it contains 4. So if you multiply that one, you choose this 0.24 or 2 SF as your final value because this is the fewest number of significant figures for multiplication and before multiplication operation. Same goes would if you divide this. So you need to choose which factor has the fewest significant figure. Then mo na yung i-follow in your final answer. For addition and subtraction, the number of significant figures are determined from the position of the first uncertain digit and with the least number of decimal places. Here, if you take this example, 84.2, you know that it's 3 significant figures. You add it by 22.321, which is 5 significant figures. So you follow the number with the least number of decimal places and the first uncertain digit and number. So here you need to you need to eliminate this 2 and 1 and follow this here, which is equal to only have 4 SF. So this is the value kani siya has the fewest or the least number of decimal places. For minus, for subtraction operation, you also follow the least number of decimal places. So this one is the least among the other one. So you convert this 0.368 to 0.37. So it's quite easy to do this. So example problem number 3, report the result for the indicated arithmetic operation using the correct number of significant figures. Also, assume all values are measurements and not exact numbers. So for example 1, this is a multiplication operation. So in the first the first factor, we have 3SF. And then here we have 2SF. So in multiplication, we know that we must pick the factor that have the least number of significant figures. So our answer should have 2 significant figures. So let's solve this problem. So 4.30 multiplied it by 0.31. The answer is 1.333. So in terms of 2 significant figure, you could write it as 1.3. Your final answer should be written as 1.3. Then here for letter B, this is an addition operation. So we should pick the number that has the fewest least number of decimal places. So 4.033 plus 88.1. So this is equal to 92.133. So we put a barrier here. We don't include this. So our answer would be 92.1. For the last number, we know that this division operation, this includes 2 significant figures. And then this one is in terms of scientific notation, which has also 4 significant figures. So what we follow is the final value that has 2 significant figures. So solving this problem, we could get a value of 3.23 3 times 10 to the power of -4. But if in terms of 2SF is just 3.2 times 10 to the -4. This is our final answer. So an exact number is a number that results when you count items or objects when you define a unit. So we always treat our measurements as inexact numbers because all of our measurements are just estimates. So, and then exact number, these are things really that usually is a number resulting from counting items or objects, and then if you define a certain unit. So these are examples. The examples of exact numbers are 10 fingers, 5 balls, then 1 meter, which is equivalent to 100 centimeter, 12 inches, 1 foot. So that are examples of exact numbers. Then for measured numbers, which are usually in our measurements, these are always these are numbers that always contain uncertainties, and this results from observations and readings. So here we have 15.3 cm, 1000.8 grams, then 0.0034 ml. So these are all examples of inexact numbers. So for our practice problems in this lecture, so I just want you to answer this practice problem. So here the following dark words illustrates the type of errors often seen in measurements. So the bullseye represents the actual value, so the center down here, and then the darts represent the data. So the question is that which experiments yield the same average result, which experiments displays high precision, which experiments displays high accuracy, and which experiment shows a systematic error. Then for number 2, carry out each calculation, paying special attention to significant figures by rounding the numbers, and then also given the exact units. So you just need to solve these letters to answer. Then in the final value, apply the proper or correct number of significant figures and the units. So I guess we're done in our discussion. So thank you for watching the part 1 of this topic in numbers and measurements. So the next video will be the part 2 of this discussion. So if you want to submit your work, just email me in this. Just email me here, and then you can also reach out for me, and then we could talk about the things that you don't understand or you understand in this lesson, and then yes, thank you for watching, and then I hope to see you on the next one. Thank you. Bye everyone.